see some of you in the background, some of my colleagues. It's it's really awesome. So thank you for being there as well. So I'm going to talk about cogitate, the complexity chasm. So now cogitate is a weird word, right? It just means to think deeply or reflect about it. And what I want to reflect on is using systematics, especially on large language models. What is really happening here? Because there's a lot of unknowns and uncertainties that we don't understand that is happening. I'm currently part of KO Lerva, which is in Belgium, and it's been quite a journey moving to here from ESCOM as well. But ESCOM has empowered me to be here today, and that's also why what I want to acknowledge. All the stuff I learned in ESCOM was super amazing for what I'm doing now. So let me go into the presentation. So what I'm going to talk about is really understanding the exponential evolution of large language models. And large language models means that they've only been trained on words. They have not seen they've not seen number, like in terms of they haven't seen pictures, they just seen words. They've been trained on information that's on the internet, but it's just words. They have never seen pictures. And that's very important to remember. So GPT, what most people are using GPT-4 on the surface level, if you look at the iceberg, a lot of people are using it to construct emails, which is brilliant at. It can write news articles or even read them for you. It can give you some ideas for gifts and even do some of your assignments for you. And that's great. Like a lot of people are using this very successfully. I mean, there is a lot of biasness, like Dr. Witta mentioned, which we should take into account, but it's pretty good at these things. And that's why there's such a high adoption rate, because you all need to do these. And yes, we can do them, but it can do it so much faster than we can. But under the surface, well, these are the visible things that we often use every day. But under the surface of this iceberg, there's a lot going on, which we don't understand. One of them is from this article from Wei et al. In 2022, where it shows that as the model size increases, these are the number of parameters, 10 to the power of 18, 10 to the power of 20, 10 to the power of 24. Suddenly, out of nowhere, it seems to be able to do arithmetic. Now, this is important to remember that these models have only been trained on words, on sentences, on what it's read. How is it suddenly being able to do arithmetic? Or it's trained to do word unscrambling. It's trained on data and the way that the training is in English, but suddenly can answer questions in Persian. Where is this coming from? And why is it a sudden jump in ability at a certain parameter size? And that's kind of what I want to use system dynamics to explore a bit with. The most interesting thing about this for me is that in 2018 and 29, well, basically the theory of mind. Now, for those, most of us don't know what theory of mind is. I also didn't. So when I looked it up, it's really about the ability to understand another human being. When I think about anyone in the room now, or I just think about another human, I have the ability to think, to imagine what they are thinking, and that's why I can respond in that way. Now, nobody thought about this, but in 2018 and 2019 there was no theory of mind. 2020 it had a theory of mind about a 4-year-old. 2022 in January it had a theory of mind about a 7-year-old, and about a year ago, 2022 November, it had the theory of mind of a 9-year-old. This was still ChatGPT 3.5. It's not 4, and this is a year ago. Do you know when we figured out it had this ability? Only in March this year. So it really had this ability, but we didn't know. We didn't know even what to measure. We didn't even think it could exist because it's just learning from text. So why would it have this ability? Why is this happening? And I'm going to try and use some basic systematics to kind of explore this with you. Okay. So this is the invisible parts that we kind of maybe want to explore a bit more. So driving a bit into the depths of LLMs, it started with very basically asking this simple question. The cat sits on the, what's the next word? Can you complete that? It's very easy for us to do that. The cat sits on the mat. Like it's a very trained response that we've been given. And that's what we try to do with natural language processing. That's where AI kind of started, like ChatGPT 3.5. But it going back further, in 1957, about the same time as dynamics started developing, that's where we discovered the perceptron model, which is a very basic neuron, and it's a basic equation where it's basically W times x1 or the W times the x's and all counted together going through an activation function to produce one output. This is a very simple linear function, and it was great because it could show, oh, we can actually create any linear function using this method. But that was all it was good for. So we experienced there often AI winter. Nobody saw really the value of doing that. We have so much better equations to model things. But in the 1980s, then we discovered the multi-layer perceptron. So it's like multiple levels of these, and like you can see, all of these circles are one of them, and they're all connected. And what we discovered back then was, oh wow, okay, now I can actually not just do linear equation, but non-linear equation. So it's a general equation fitter. But what we found was it needed so much data and so much computer powering that we didn't have that back then. So we experienced another AI winter. And then in 2017, like recently, we discovered transformers, which combine this multi-layer perceptrons into bigger models. Each one of these little blocks, like these feed forward, is one of these elements. And it combines with some more mathematics to encode and decode, as well as stabilize the network. When you use this is what we call transformers. And that is where GPT comes from. I'm saying this because I'm currently doing a lot of courses on AI, so which is mind-boggling for me, but this is the basics of how it transitioned. So giving you that background, what we discovered recently, and this is 2020 and 2021, 2022, that at a certain parameter size, when these circles get to a certain number, like very, very, very big, and look at these numbers, there are billions parameters in billions. We didn't have this type of a technology before to actually simulate this effectively in training it. But then it starts developing abilities like addition, like a benchmark toxicity classification. It can start developing these abilities as the models grow in size. What this does is it opens up doors to new innovation, once deemed to the realms of science fiction. Now, to prove this point, is look at this article. This was from Meta in October this year, just basically a month ago. Meta was also called Facebook before, towards a real-world decoding of images from brain activity. So what they did was they put a headset on. It's not even intrusive. They showed an image to a person, and then they used the brain waves to decode what that person might be thinking. And let me see, on the left-hand side, this is the image they showed. On the right-hand side, this is the predicted image. Now, this is scary. It's not perfect. There's a lot of like flaws in it, but you can see tiles in both. You can see a basin. You can see the mirror. It's very clear that, I mean, the technology will just get better from this point onwards. So what is happening here? Well, how is it developing these abilities? So let's look at the method that I followed to kind of just understand a bit better. I use this and simplified it grossly to just understand what could be leading to some of this. So the assumptions I made was to build a basic, understandable, and manageable representation, but that still encapsulates the fundamental dynamics around complexity and performance. It assumes monolithic entity for complexity, which means that we just look at parameter size as the definition of complexity. It's much more detailed than that, but for this simple model, that's the assumption I'm going to make. And then accuracy is the other stock, that at certain points, the accuracy starts increasing. What it came out was the threshold points. At some stage, the complexity starts happening, and that's depending on a complexity effect. And then Moore's law, where every 18 months, we see a doubling in computer size or complexity, and we've seen that happen consistently. So this is the very basic simulation. And even at this basic level, I want to bring to you some insights and the power of system dynamics to very simply really show us some kind of insights, which I think is applicable. So simulating the basic model, there's two variables on this side. You can see model complexity, this is the red line, and it constantly increases. It looks like there's nothing here, but it's just because it's growing so much at the end that it looks like there's nothing. And the blue line is the model accuracy. And this you must think about a specific ability. At some point, suddenly, it jumps and has ability. Now, happens when the complexity threshold effects are between these two numbers. And at this scale, the change seems to be instant at month 840. The model complexity keeps on growing in exponential in size. Like that's the thing we don't see. As a general population, we don't see that, but we do see the blue line. Suddenly there's something. If we zoom into this blue line, actually, we see that it wasn't just an instant growth. There was an S-curve. And if you look at the months period, it's a few months. It didn't just happen instantly. But looking back, it might have seemed that way. So if you focus on those months, you see that the S-curve shows an accuracy ability, and exponential growth in complexity still keeps happening. And for me, this links to what we saw earlier in the presentations, that there is a constant growth, but we don't always actually notice it. The way we measure accuracy is why there is a start and an end. This is a counter argument towards this whole idea that these models are developing abilities. They're not. It's just the way that we are measuring those abilities that make it seem like suddenly develops it. And we shouldn't negate that effect of measuring these abilities. Before this time and after this time, it seems like there's nothing changing. And I think that's when we see the AI winters happening. So is there another AI winter coming? I'm not sure. But depending on, like, looking at both the two presentations before, it's very possible when people don't, when there's no new thing that they're seeing. So then doing a bit of a sensitivity analysis on when those abilities, which are different, may emerge, we can see that if we vary those complexity effects at which those abilities starts happening, the initial ones happen quickly and very fast, like the ones we've seen the past year suddenly start emerging. But there are more things happening. There are more abilities coming out. The large distribution of abilities are unseen, and yet they are growing. And we only become aware of them when they reach a certain point. Before they are accurate enough, it's like they don't exist to us. We only see these lines when they are at high functioning levels. Before that, the model has the ability, but it's not really seen because it's not accurate enough for us to use. What I want to bring back to our conclusion then is that in S2, we kind of used a very basic structure to really show us that the unseen complexity is constantly growing, but that's not the variable that people are interested in. They're always interested in the functions, and those functions emerge at a very different rate because of the way we measure it. It's not the real thing happening. So there's a threshold of complexity where this happens, and we don't know what that is. We don't even know what those abilities are that's coming. So what I think is really important for us as humans to recognize is that it's both a slow and a fast process. It's slow because the complexity keeps on developing at a specific space, and it's been doing that for decades. But we only start noticing it. And when we do start noticing it, it's already at that S-curve point where it's growing exponentially. So then it seems like, oh, it's growing so fast, but it's actually been there for a long time. Our blind spot as humans is that we really struggle to understand the exponential function, and that leads us to always take a proactive response. And as you can see, these abilities are going to be part of society, and we're only going to realize it after it is part of society. So bringing it back to my final thoughts is then leaving you guys with a question, and my own question, because I don't know exactly how to answer this. How do we cultivate the foresight and wisdom to ensure that the future we're building is one that remains aligned with our human values and aspirations? Because these things are just machines. They don't have values. The values they have is the things that's been trained into them. So we have a responsibility here. And I think part of it is really embracing what makes us human, what makes us different to machines. And we really need to do that for a future to be good. Okay, so that's my main presentation. Thank you so much. I don't have anything else. If there's any questions, I'm here. Just go back here, stop sharing. Good.